Hey guys, how's it going? How's it been so far? Awesome, cool. So my name's David. I'm a software engineer at Facebook. And today I wanted to talk about techniques for streaming 360-degree video and the work that we've been doing to try to make that a reality. A little bit about myself. I'm very, very passionate about video. I work on video. Past jobs I've worked on video. And I think even before working on video, I've had a really strong passion for video and video compression. Back in the day, I used to do things like rip TV shows and DVDs and compress them, and the idea that you could get something that was physically impossible to fit on any storage medium or anything like that, and now I could fit them all and burn them on a CD or a DVD was pretty cool, and I thought that was really impressive. I remember one of my cable boxes had a FireWire port where if you plugged it in, you could actually stream raw video straight out of the cable box, and that was pretty cool, and I would compress all of that stuff. And there was an internet forum called Doom9. And I don't know if any of you have ever heard of that. Yeah, right there. So I would just read that and just read what everybody else was doing and be like, this is amazing. There's a community of video compressionists that were doing stuff, and maybe one day I could do something like that. So I want to start this with a little bit of a story. I'll take you way, way, way back to 2004. And in 2004, two things happened to me. One was I got my first HDTV. So how many of you guys remember getting your first HDTV? Show of hands. So mine was a 27-inch CRT tube HDTV. And the thing weighed like 100 pounds. And I was in college at the time, so I was carrying that thing up and down stairs when I moved apartments and stuff like that. And it was a pain. But it was worth it because it's your first HDTV. And the image quality is amazing, all this stuff. The second thing that was really important to me in 2004 was when the TV show Lost came out. So now I had the combination. I had the TV show Lost in HD, and I had my first HDTV, and I turned it on, and I watched a couple episodes, and I was blown away. The jungle scenes, the color, the clarity, the crispness was amazing. I had my wow moment. It was awesome. So fast forward a couple years, and I get a new HDTV. I get this 55-inch LCD HDTV. It's actually lighter than the old CRT 27-inch that I had. So I did what I did then. I turned on Lost, this time on a Blu-ray, so it's even better quality, and I expected to be amazed. I expected to be awesome. But in reality, what happened was something like this. The super sharp image that was really awesome on my 27-inch TV stretched and became blown up, and suddenly every single imperfection, every macro block error, all the graininess, everything like that was magnified. And so it kind of bummed me out a little bit. I was expecting another wow moment. So with 360 video, this is video that's all around you. Everywhere you look, you turn your head, or you scroll your mouse, or swipe your phone, or something like that, and you see video everywhere you go. And you watch that on your laptop or on your phone, and you say, this looks amazing. I can move it around, and it looks awesome and high quality. Now, I want to load that in my head-mounted display, and again, be amazed. I turn my head, and I see everything. But you get the same kind of thing. It's actually super blurry, right? I don't know if any of you have ever tried to stream existing 360-degree video to your head-mounted displays, but when you're streaming it over network, sometimes it doesn't look that hot. Sometimes you can't even tell what's going on. Again, all of the compression artifacts, all of the noise, all the graininess comes out to you because the things that you're looking at, if you take a 4K-sized 360 video and you put it in a head-mounted display, you're actually looking at something about this size. And by the way, it's about 2 inches to your face. So that's the core problem. That's the main problem. So how do we solve that? And there's two ways that we could try to solve this. One is you bump up the resolution higher. So that way you can get more detail, right? You're looking at these things super close. You need higher resolution. For us, we think an acceptable trade-off between high resolution and the ability to actually stream this thing is probably about 4K. So we target something like 4K, 60 frames per second, something like that. The second thing you need to do is really bump up the bit rate. what was an acceptable bit rate or an acceptable quality level watching on your phone or on your computer is no longer acceptable in a head-mounted display. And again, this is because it's right up on your face. So you have to do those two things. So that, of course, makes this thing almost impossible to stream. And we have 3 different ideas to try to help with that. And in reality, it's going to be something like the combination of multiple ideas that really chip away at that bandwidth problem to make this achievable. And like I said before, we were targeting something like 4K at 60. And generally, in our tests, to get kind of an acceptable quality experience in a head-mounted display, probably you need about 30 megabits per second at a minimum to achieve good quality. But average typical home Wi-Fi, at least in this country, is about 5 megabits per second. So there's like a 6x bandwidth gap that we need to overcome. So let's talk about compression for a second. And let's dive in a little bit. I think I got a little bit ahead of myself. But 30 megabits is what we need. 5 megabits is what we have. So what can we do in regards to compression? Where can we go? Typically, the most popular compression standard right now is H.264, main or high profile. And that works pretty well. It's very well supported. It's awesome. But there are things that we can do to improve this. The first thing that we can think about is moving to 10-bit color depth. Most videos right now are encoded at 8-bit color depth per channel. If you move to 10-bit color depth, all of a sudden, you're not representing colors, 256 levels of color, but it's 10-bit. Don't know what that at the top of my head. The advantage in image quality is that you no longer get banding. So what you'll notice that's very common is when you look at scenes like a sky, you'll see color banding. When you move to 10-bit, that goes away. So that's awesome for image quality. But the nice thing is it actually compresses better, too. In our tests, what we've seen is that moving to 10-bit color depth gains you about 5 to 6% reduction in bit rate. So that's pretty cool. And that's something that we want to do. But there's a problem. The problem is that there's practically nothing that can decode video with 10-bit color depth today. This problem is going to be solved in the future. Next generation of devices will support this. But right now, that's kind of off the table. The nice thing is we know that it's going to quickly become on the table. The next thing we can do is try to explore new compression algorithms. Like I said, H.264 is kind of what's popular right now, but there's HEVC, there's VP9. Those things are out now. They work, and they achieve maybe like 30 to 40% bitrate reduction. So that's awesome. Again, there's a problem. Those compression tools are super slow. They're a lot slower than existing H.264 compression tools because these codecs are more complicated. They have more tools to really squash the video and things like that. And so they're really slow. It doesn't mean it's going to get, it's going to get faster in the future, and computers are going to get faster. So this problem kind of goes away over time. But it kind of makes it unfeasible to use right now unless you have a lot of compute at your disposal. Other tools that you can use in your video compression toolbox are things like multi-view coding, which for stereo video, especially stereo 360 video, instead of putting the left and right eye side by side in one video stream or top and bottom, they're actually separate streams that reference each other. And you get some compression efficiency that way because you kind of hint to the compressor that, hey, these are just left and right eye, they're super close in image, they're just a little bit offset, and they're separate streams. The advantage there, beyond that, is that because they're independent streams, they can fit better into hardware decoders, right? So if you have a 4K video left eye, 4K video right eye, and you pack them side by side, it's super wide. Or if you pack them top and bottom, it's 4K tall. And that becomes a problem with today's hardware decoders. So splitting them up is really cool. Other techniques are things like multi-view. Not multi-view, scalable video. Scalable video, you can kind of think of like the progressive JPEG of video, where you layer on additional quality as different streams. And this kind of nets you some gains too. You only need to get to the quality that you want to have an acceptable streaming experience. So there's all these tools. There's all these things you can use right now. Again, there's some disadvantages. Some of this stuff is not supported in hardware decoders today. I don't think scalable and multi-view is supported natively in a lot of stuff. So you kind of have to build your own players. But like I said, in the future, adoption is going to be great. So this gets you some of the way there, but it doesn't really get you all the way there. So let's talk about warping. Let's talk about how do we change the video itself so that it's actually easier to compress. If we can do that, we can get some gains. And I like to talk about the equirectangular projection. If any of you have downloaded these things, you're very familiar with this. This is typically how most 360-degree video is transmitted today. And you can kind of think of equirectangular projection as a map of the world, right? You take the sphere, you take the globe, and you unwrap it, and you stretch it, and you put it on a rectangle, and you hang that on the wall in your classroom, and that's your map of the world. That's your equirectangular projection. It has disadvantages. Stuff at the North Pole and the South Pole are super stretched, right? And distorted, and in no way reality. There are other projections that kind of help this. You know, the Boggs eumorphic projection attempts to accurately portray the land masses, but then it leaves gaps, right? You see these little black holes because we're not warping anymore. And that leaves to wasted space if you're going to encode a video that way. So it's a problem. And here you can see it kind of amplified, right? Antarctica is not this thin strip of land that's super wide. It's actually more of a normal body. Another problem with this, not just the stretching of the video, is that it's a video. It's not an image. So what that means is that tiny movements at the North Pole and the South Pole in your video actually result in super large movements in the equirectangular version. In addition to that, those movements are not straight. So if you're moving in like a straight line, but you're near the poles, in the equirectangular version of the video, it actually curves a little bit. So all this additional complex motion makes the video harder to compress. And we want to get rid of that. So the most obvious way, I'm sure many of you know this, is don't think of it as a sphere. Try to think of it as a cube, right? Try to project that spherical video into a cube mapped version. And the way that you do that is you take your equirectangular video and you cut it up into the sections that represent the faces of the cube that you would be sitting inside. You do the transformation so that the faces of the cube are actually representative of what it would actually be when you're in there. And the other step that we take is that we rearrange the faces of the cube, kind of like a tile puzzle, so that it fits nicely in a rectangle with no wasted space. And you'll hear me talk about that a lot. We don't like wasted space because it just takes up, like you're just encoding black, and what's the point? So that's super nice. The way that we do that is, I had the image of the sphere and the cube together. What we actually do is we draw a line from the viewer through to the sphere to get the color sample, and then where it lands on the cube. So in some cases, it actually maps to a couple pixels that were on the sphere. In other cases, especially near the corners of the cube, it maps to a lot more pixels that were on the sphere. And so we take the weighted average to compute what the final cube map would be. So that's what we think is pretty good to, one, reduce that stretching at the north and south poles. And in fact, when you transform an equirectangular video into a cube map video with the tiles moved around, you actually achieve about a 25% reduction in the number of pixels. And second, you remove that warping. You remove the nonlinear motion. The motion is more accurate and representative of what's actually going on. And this compresses better. So I talked about compression. I talked about transformation. Are we there yet? Is this enough to get us to an acceptable streaming experience? Probably not. We need more. And what we need to do is think about the fact that when you're watching these 360 videos in a head-mounted display, you're actually only watching a subset of the video. You don't actually care about the parts behind your head. You don't actually care about the things that you're not looking at. So why do we expend the effort of streaming that to you? Why do we take that bandwidth? And we call this viewport adaptivity. So with viewport adaptivity, you can think about you're looking at this thing in your head-mounted display, and you look to the left, you look to the right, and things look pretty good because your viewport has a nice high-quality image. But if you look really far to the left or to the right, you either see super blurry or low-quality video or no video at all. So this is the idea that the parts that are out of your field of vision are either gone or low quality. For us, we kind of chose to take a low-quality version because there are times when you spin your head super fast and we don't have a chance to catch up. So it's better to show something than nothing, in our opinion. But I want to spend a little bit and talk about network latency in that regard, right? Because if you're only streaming down a portion of the video that somebody's looking at, you kind of have to be able to adapt very quickly. And there's two solutions for this. One is real-time transcoding, right? So as the server is sending you the piece of the video that you're watching, you are also streaming back to the server your head position, where you're looking at. And you do that in real time. And then the server can then take that original source video and retranscode and crop and transform just the part that you're going to look at and stream that to you. And that works really well. If you can do that in real time, you end up having a nice tight viewport that minimizes bandwidth loss or the excess. And it works pretty good. But there are some downsides to that. The main downside that we see is that it takes a lot of resources, right? So for every person that's watching it, the video, every person is unique. They're going to be looking in different directions. They move differently. What they care about in the video is different. So because of that, you kind of need to retranscode on the fly per viewer. And that's super expensive. And it doesn't scale to like thousands or tens of thousands or hundreds of thousands of simultaneous views. So another idea is to just say, why don't we take a set predetermined number of viewports ahead of time? We'll transcode it offline, and we'll have like 10 different viewports or 20 or 30 or something like that. And as the user moves their head, they switch between viewports. So if I'm looking straight ahead, this part is in high quality, and everything else is in low quality. And as I turn my head this way, I switch to a new video stream where this is in high quality, and everything in the back is low quality. And if you get it right, and you time it perfect, nobody notices. And it's pretty awesome. So the networking side of this is you send a request to the server, and the server does a little bit of processing, sends a response back, and starts streaming you video. In this diagram, we cut up the video into 1-second chunks so that you can kind of switch between viewports on a second's notice. So you start getting the first frame of the video. For a 1-second video, most of the data is front-loaded into the first frame because the rest of the frames of video depend on that first frame. It just encodes deltas and things like that. So you can't really start playing a video until you have the first frame. So once you get the first frame, you start playing the video. Time, 1 second. While the video is playing, you're still downloading the rest of that second of video, and it's playing in real time. Once you're done downloading that, hopefully you've downloaded it and it took less than a second, you need to make a decision. Do you send down the next second of the video portion that you're looking at? Or do you send down the next second looking in a different direction? And this is all part of the heuristic and the algorithm for trying to predict where people are looking. This is different than traditional head-mounted display, like VR's style prediction, because it's not milliseconds. You're going very far. And so it becomes a lot less accurate. So you make a decision, and you choose a viewport, whether it's the same one or a new one, and you start streaming that, and you get the next frame of that viewport. And you have to get that before you finish playing that first second. And once you do, you switch, and you start playing, and while you're playing, you download the next one. And you keep repeating this thing over and over again. So this, again, has a lot of challenges, right? You have to keep buffers very low, because there's no point in streaming 5-10 seconds ahead if the user turns their head, and all of a sudden you need to switch viewports. You kind of wasted that. You need to be very quick, and you need to stream very fast. So we're talking about very low latency, very responsive video streaming. So assuming we solve all those problems, we can say, OK, what does the viewports look like? What am I going to do to make the areas that I don't care about either gone, or compressed better, or smaller, or something like that? One way is to think about blurring the parts that you don't care about. So if you can imagine in this equirectangular video, the portion in the bottom right, or bottom left, is the part that I'm looking at. It's nice and high quality. Everything around it is super blurred. Blurred video has a tendency to compress better because it hides the detail. And if it's blurred strong enough, it also hides motion. You can see this on a cube map version, where the square in the middle bottom is kind of where you're looking at, straight on. The square in the bottom right is behind you, so it's all super blurred. And the other squares are the squares that are kind of surrounding your peripheral vision, so parts of it are blurred and parts of it are not. So when you do blurring, you kind of have to take into account how much do you blur and where do you blur. And you can kind of think of this as a linear function, where straight ahead, where I'm looking at, is 0 degrees. And as I move my hand back to right behind me, that's 180 degrees. And you adjust the blurring strength based off of that angle. So initially, from 0 degrees to some degrees out, you're still within your field of view, your eyes. You don't want to blur at all. And then after you pass that threshold, you start blurring. For us, we decided to slowly increase the strength of the blur, because if the user kind of slightly turns their head to the side, just a little bit, and then comes back, we don't want to actually try to switch viewports. It's only temporary. So we do want to have a little bit of area where they can see, and just progressively get blurrier and blurrier as it goes towards the back of the head. Again, like in this example, it's pretty linear, but it could be like a power function or something like that. It could be a step function if you wanted to get super aggressive. It could be anything. So we took some time and we played with this. We took some sample videos and encoded different blur parameters, different blurring strengths, and different field of views to try to get what the optimal regions are. So this, I think, is the next section, so let's not worry about that. So we kind of ended up with a graph like this. The x-axis is the viewport size. How wide is that clear area? The y-axis is the blurring strength. How much are you going to blur? And here, the green line represents about a 20% bit rate reduction. The red line represents about a 30% bit rate reduction. And the blue line represents about a 40% bit rate reduction. The interesting thing that you can see is that it has a tendency to be very vertical. And what that means is that as you increase the blurring strength, you actually don't decrease the bit rate too much. There are portions of that graph where it does have an impact, but a lot of times it doesn't decrease bit rate at all. So blurring is not as effective as, for example, making the viewport size narrower. And in fact, if we blow this up a little bit, you can see that these are the only areas that actually make an impact. There's a certain area and threshold where blurring doesn't really reduce bit rate, and then it starts to reduce bit rate, and then you pass another threshold, then it stops to reduce bit rate. And this can be seen across different field of views. So if we blurred, for example, half of that cube behind you with certain blurring power that we thought was acceptable, we'd achieved about a 30% bit rate reduction on top of all the other stuff that we talked about. And that was pretty good. Another thing that we tried is spatial subsampling. This is the idea that rather than blurring the parts that you don't care about, why don't you just reduce the resolution of the parts that you don't care about? So you can kind of think of the front half again, the front half of the sphere, or the front half of the cube, and the back half of the cube. And how we accomplish this is, if you take this cube map version of a video, you divide it so that you have the front and back half. And here you can kind of see, this is the front and this is the back. I've kind of unfolded the flaps. Then reduce the resolution of the part that you don't care about. And finally, reassemble it all again so you have no wasted space. It's packed, it fits nicely, and it's just pretty nice. So the results of spatial downsampling look something like this. And if I go forward one slide, you can see the blurred version. So if I go back and forward, this is blurred. This is spatial downsampling. Blurred, spatial downsampling. It looks pretty good. Like, to the naked eye, to the untrained eye, you can't even tell. Obviously, in a display, in a head-mounted display, when it's really close to your face, you can tell. But the interesting thing is, we achieve the same bitrate reduction by reducing the resolution of the back half of the sphere as we did by blurring the back half of the sphere. But the quality difference is astounding. It's awesome. So, cool. 30% bitrate reduction. You can even combine these techniques together. We tried that, but we saw that the gains you achieve from that are not as impressive. I mean, you've already reduced the resolution. Blurring that smaller thing helps, but not too much. We even tried reducing the frame rate of the parts that you're not looking at. So you can imagine the back half is, if the front half is running at 60 frames, the back half is running at 30 or 15 or even 1 or something like that. Again, we found that the bitrate reductions were not as impressive as the resolution when you reduced the back half of the sphere, the spatial subsampling. So what we came away from with all this experimentation was that kind of reducing resolution matters more than anything else. It's the most impactful, right? There's no better way to save bandwidth transferring pixels if you don't transfer pixels in the first place. So what else? Like, coming away with that knowledge, when we thought, okay, how do we think of other ways to not send pixels rather than making pixels easier to compress? How do we take advantage of the fact that the part behind you, the part that you're looking at, doesn't matter, whether in a sphere or in a cube? How do we think outside of the box, or think outside of a cube in this example? And the idea that we came up with is to not think of it as a cube, but maybe trying to think of it as a pyramid. So if you take that cube that your head is inside of, and you take that back plane, and you shrink it down to a single point right behind your head, you end up with something that looks like what's on the screen. The front face, the part that you're directly staring at, is super high quality. It's actually the base of the pyramid. And the sides of the pyramid wrap around your head back to a single point. This has the nice property of the sides of the pyramid naturally reducing resolution because it gets smaller as it goes behind you. So it's super cool. And if you unwrap the sides of the cube, you end up with something like this. And then we shrink it again to make it nice and rectangular. again, so there's no wasted space. There's nothing that we don't want to encode anything wasted. So it kind of looks something like this. The area that you're looking straight on, again, is super high quality. And the parts behind you are very warped and distorted. Something to talk about here is that we talked about with cube maps, you reduce the distortion. With the pyramidal transform, you kind of reintroduce some of that distortion. But you've reintroduced it in an area where you're aggressively reducing the resolution. So the trade-off is actually worth it. So that's kind of where we're at today. This gives us a lot more bitrate reduction because you're naturally reducing the resolution of the image. In fact, if we take, for example, like a 4K equirectangular video, and we convert a viewport into something like a pyramidal, it becomes less than 2K, less than 1080p video. And this is something we know how to stream over Wi-Fi today. This is a solvable problem. So that's pretty awesome. And you end up actually getting the native resolution of that 4K video in the part that you care about. In fact, this fits under the limitations of current hardware decoders. So your phones, your DVRs, and things like that. This allows you to actually play back in hardware even larger videos. Right? So if you took a 6K equirectangular and applied a pyramid transform, you could actually play back in hardware. If you took an 8K equirectangular video and applied this transform, you could play that back in hardware. You could actually take 6K stereo equirectangular, apply the transform to each eye, and then pack them side by side, and you can play that back in hardware. So that's pretty cool. We think that's awesome. We're also playing with a little bit, other projections. The idea is like, okay, if we turned it into a pyramid, like what else can we turn it into? What other geometries are really good for improving compression efficiency? Things like turning it into a cone or turning it into a teardrop or something like that. We've messed with those. Conic improves compression efficiency a little bit, but it introduces other artifacts, so we're still working on that. We think pyramid is pretty cool. So again, if we think back to the problem, we need 30 megabits. We have 5. How do we chip away that problem? If we apply these techniques, like these multiple techniques and stages, I don't think there's one silver bullet. But if you do all of these things like in tandem, you actually can get somewhere close to that. It's actually achievable. You can start streaming this stuff in super high quality with low latency. But again, it's not, I don't want to say it's not a solvable problem, but the problem gets harder, right? So this problem statement is, how do we stream a monosphere at 5? If you turn into stereo, you've kind of doubled the problem. The next generation of head-mounted displays get higher and higher resolution. Now you talk about how do you stream what was originally a 6K equirectangular video or an 8K equirectangular video or even higher at 5 megabits per second, which is home Wi-Fi. That's super hard. And so over time, the problem gets harder. But I think we can solve this together. I think as a community, if we think about how do we compress video more efficiently, specifically how do we compress video that we know is going to be displayed in a headset, how do we make that more efficient? It's absolutely solvable. And it just takes time. The other thing to think about is that as we as a community are working on how to make this video smaller and smaller and more compressible, there's other people working on making your home Wi-Fi, your bandwidth faster and faster. So there's two different sets of people working on the same problem, burning the candle at both ends and meeting in the middle, and we'll get there. So I'm trying to think of, is there anything else that I missed that I want to share with you? Why don't we just open it up for questions? you guys come and ask a bunch of questions. I think there's a microphone or something like that where we can.
And the microphone is right here, so if you come to the mic and say your question.
Hi. Microphone's here, but there we go. I'm Devin Copley from Kaltura, the video streaming platform, working on some of this stuff as well.
Hey, Devin.
I have a couple questions. First of all, with the pyramidal projection, is the suggestion there that you would actually create multiple separate assets and switch among them in the head head-mounted display dynamically based on where the user's looking, or are we just giving up resolution in one half of the sphere?
Well, so I think you can do this two ways. One is if you just give up resolution in the back half of the sphere, then what you need to do is tell your content creators, hey, the best thing you should be doing is focusing and placing the things that people care about right in front of you, and they can turn around and get the full effect of seeing all around them. But really, the subject matter is right in front of them. The other way is you do kind of make a bunch of different videos pointed at different parts of the sphere, and you switch between them. And if you do it right, the user never notices. The suggestion to the content creators there is, hey, there's only going to be a section that's in high quality. So as you're thinking about how to place the important parts of your scene, try not to make things move very fast, across field of vision, so people have to track it and things like that. Rather, if they just turn their head, you switch to a new viewport, you see something very high quality. You turn your head to look at something else, you see something very high quality. Whereas if you're continually trying to sweep, depending on networking conditions, then you may start getting into that low quality region, which is better than nothing. It's better than black, but it's obviously not advised. So I would say until it's perfectly solvable, the thoughts are, you have to kind of frame and stage your content in such a way that, it suits the technology.
And one more question, if I could. There's an inherent problem with all current video codecs that I know of, which is that they're based on a frame with edges. Mm-hmm. And in fact, there's no edges in a 360 video. And ideally, the compression algorithm ought to be able to take advantage of the fact that something moves from one side of the fake frame to the other side of the fake frame and compress that accordingly. But current algorithms can't conceive of a sphere.
Yeah.
Is that something you guys played with at all? Did you get down to that level, or is that too far in the future?
It's something we've thought about, but not necessarily something we played with, right? Because if you talk about for simplicity's sake, the original Equirectangular version, right? You hit the edge, and you're actually just wrapping around to the other side. So your motion vector is not necessarily I'm going way to the opposite side of the video. I'm actually going just one block over, which happens to be on the other side. It's a good thought, right? It's something that we should take advantage of, at least for like an equirectangular projection or like a conic, or like a cylindrical or something like that. When it comes to cube maps and things like that, then you have to be a little bit smarter and say
right, then it gets more complicated.
Yeah, it gets more complicated. What's to your right may be a different part of the video down here. So you kind of have to hint to the compressor that that's how things are.
But to some degree, the whole projection thing in the first place is the fact that we're trying to map a spherical image onto this flat, planar, design of the compression algorithm in the first place.
Yeah.
Anyway, it's just a question.
Yeah,
Thanks
absolutely.
very much.
Yeah.
Let the next one go.
Thank you. My name is Jason Spersky from Zeality.
Hey, Jason.
I actually was just going to ask more for some context. In the recently announced Facebook 360 player, how many of these technologies are being leveraged and how many are slated for early or new releases? And then kind of part of that question, how many of these technologies is Facebook looking to implement into their video processing for uploaded video and submitted video?
So right now, the way the pipeline works is that users upload equirectangular video with some metadata associated with it that says, hey, this is actually a 360 video, it's equirectangular, et cetera. And then in our pipeline, we do the transformation currently to a cube map, and then play that back. With resolution that's high enough, and not absurdly high, but just high enough in a cube map, that's good enough for things like desktops and phones. It's not necessarily good enough for, in a head-mounted display or something like that, in a headset. So We are actively thinking about that. The pyramid work that we talked about is like a direction that we're still researching and going forward. Our pipeline is set up such that when you upload a video, we actually encode multiple versions, typically at different bit rates and resolution. And so it's a natural extension to say, hey, I want to encode a couple cube maps. I want to encode pyramids in 30 different directions or something like that. And then it'll all pop out in a nice manifest.
Hello, my name is Andrew Andrew Johnson from DRASer. I
Andrew.
was curious, you had mentioned the requirement to have very small buffers for when you're doing either real-time transcoding or even if you're doing a bunch of offline versions from different angles.
Yeah.
When you have smaller buffers, you're more affected by things like packet loss. So I was wondering if you have found it necessary to do things like forward error correction inside of the encoder where you're actually including redundant data so that if there is packet loss, you can handle that, or if
Right.
packet loss has not been something you've really dealt with too much yet.
Right, so for myself, I'm not like the networking expert. I look more into compression and stuff like that. But it is something that's important, right? So if you lose a packet, you're blocked, right? And you have to, in current, if you're streaming over TCP, you have to wait for a retry. And typically when you wait for a retry, the server slows down how much it's going to ship to you, and you have to wait till it speeds back up and things like that. So a lot of video streaming transports today are built on top of UDP and incorporate things like FEC. And those kind of products exist out today. We could take something off the shelf and do that. I think that works pretty well. There are people that are looking at that kind of stuff and seeing like, what can we learn? What can we learn about the characteristics of networks so that we can enable better streaming without retries? FEC is certainly one of those things.
Well, and then one other quick question. Have you guys played with like figuring out the optimal number of different angles that you render to?
Yeah.
So that you can switch?
So the optimal number kind of depends on a couple things. It depends on the maximum field of view of the headset that you're wearing, right? It's different for different kind of devices. It also depends on user behavior. Like, as I was saying in the talk, a lot of people kind of turn their head like, oh, I'm in a video, and then they go back to looking at what they're looking at. So it makes sense to make your field of views wider a little bit. If you make your field of views wider, you need less, overall number of viewports in different directions. So that's one kind of variable, one lever. The other lever is, what are your networking conditions like? Right, so if your latency is really high, you kind of need to, by necessity, you have to buffer ahead. And so you may want even larger viewports or something like that. Whereas if your latency is super low, you can get really tight and not have to worry about that. So you have smaller viewports, but more of them or something like that. So it's really a combination of multiple variables. So the nice thing to do would be maybe encode, different versions for different conditions, I guess you could say.
Hi, Michael from Viridio.
Hey, Michael.
Hi. Have you done any work with audio compression?
Can you repeat that? Audio what?
Compression. Audio compression.
So not me specifically and not my team specifically. So the idea would be things like staged audio or like 6 degrees of audio, or you're talking about like 360-degree audio, right? Or are you talking about any other just audio compression in general?
You're talking about video compression, and
Yeah.
a component of that is usually audio.
Yeah. So we haven't really done much there. I would say that like the bandwidth is dominated by video in this case. So it made more sense for us to invest time looking at how do we chip away at that. There will probably be a time when you do chip away at audio as well, and we can focus on that. But there's nobody on my team that's working on that right now.
Okay, thank you.
Hello, I'm Denis Ivanov from Little Star.
Hi, Dennis.
What do you think about light fields technology, light fields video? Because where you can just move your head slightly and
Yeah.
perspective it changes.
Yeah, I mean, I think light fields are super cool.
Did you do any research on this? planning?
We're aware of it, and we're kind of, I am personally daunted by that challenge, right? Because instead of, basically you have, well, in certain implementations, you have multiple cameras, like a lot of cameras or something like that. But regardless of how it's implemented, your bandwidth requirements explode, right?
Don't you think the video what we are filming right now will be replaced in future with light field video? Because right now your head stick in one position,
Right.
and it's not full too immersive for people. So I think
Right.
maybe it will die pretty soon. Maybe when light field technology will replace it completely.
That would be cool if that happens, I would say. I think we have to overcome, even with light fields, just the streaming requirements. Like nobody's gonna wait to download like a multi-gigabyte video, light field video that ends up being 10 seconds long, and they can, like, some people will, I would, but if you're talking about trying to get 1 million people watching it or something like that, it's gonna be pretty tough. So I think there needs to be a point for, again, bandwidth to increase and us to figure out ways to better compress light fields. And if we can solve that, I mean, that's a different talk, right? That's a different challenge, and it would be awesome. And now we just watch all the videos and record with light fields.
Okay, thank you.
Hi, it's Arya from PCPVR.
Hi.
Yeah, it's interesting. We have very similar ideas that I've been working on, and I was impressed that I saw very similar stuff. Very impressed with the low-res, high-res rectangular things that you did.
Mm-hmm.
So I had a question. With the cube map, you're going to have introduced edges to the video that didn't exist, especially with the low-res, high-res that had more edges.
Right.
So did you have any problem with seeing these edges?
Yeah. So this is one thing I forgot to talk about. When you convert to a cube map and you unwrap that cube and you unfold it, if the edges of the polygon match the edges of, perfectly fit where the textures are, you end up not really seeing that many artifacts. But because we did that tiling where we move things around so it fit into a rectangle, or with a spatial subsampling case where we really move things around just so it would nicely pack, the video doesn't, the pieces of the video map to different parts of that cube. And so when the video compressor takes a look at it, it has blocks side by side in the rectangular version of the video. And that kind of introduces some artifacting when you take those pieces, cut them up, and put them onto a cube, and you see those edges. So the way we solved it was we did a little bit of, we call it like overscanning or something like that, where we actually increased what would be in the cube face by a little bit, like say like 1% or something like that, and encoded that in the rectangular version. And then on playback, we shrunk it down a little bit. So we have a little bit of, you can think of it as like a little bit of padding, for each polygon face, so that when you reconstruct the cube and play it back, you don't see those artifacts. You can't see the line where the polygons join and things like that.
So and that padding is black or it's gradient to the next?
Can you repeat that a little bit louder?
The padding that you added, is it black or just a gradient to the next?
So it's not black. It's actually, we just increased what would be that cube face from the equirectangular video. So normally, you would say this region of the equirectangular video is going to be this face of the cube, and we just increase that a little bit. So we take a little bit extra of the video, of the original equirectangular video, and use that for padding.
Well, another related question, do you think any of this stuff would someday be supported in the hardware? I mean, would you have a hardware decoder that decodes cube map or something like that, or encodes cube map? Or is there any benefit?
Could you
Well,
more detailed about the question?
Mapping and all this stuff, the padding stuff that you added.
Mm-hmm.
I'm saying if there is a hardware decoder or an encoder that has parameters to know that, for example, it should search in this area, not go to the next queue,
Mm-hmm.
things like that. I mean, I'm just asking about hardware decoder support for video. That's basically.
That I don't know, and I'm not sure if I fully understand the question. You know, most hardware decoders think of video as a rectangular video, and that's it, without any knowledge of what the contents are. So you can hint to
You have
encoders.
MVC right now. Someday you might have another extension.
Oh yeah, so you could have multi-view with 6 views with each is the different face of the cube or something like that. Yeah, I mean that could be a natural extension of things, but whether somebody would support that, I have no idea.
Okay, thank you.
All right.
Hi, I'm Mike from VR Video.
Hey.
I'm wondering if you've done any work on compressing depth maps, like the type of thing you might get from computing stereoscopic disparity from something like Google Jump, or directly from something like depth sensing Connect sensor.
Yeah. So I have not, but it's something that we talk about. So we know what the problem is. Like, we want really high quality video that's all around you, that's properly projected, that's in stereo and everything like that. We're taking things one step at a time, right? So we actually have this interesting dynamic where it's like, how much time are we going to spend researching, and how much time are we going to spend like engineering a product, and where's that line? So it's something that we've talked about, but not something that we've actively researched.
Thank you.
Hi, Mike Vesta from StreamVR.
Hey.
I was wondering how much computing power you need to do this in real time. Like, is it viable to do for live streams?
So real time, I mean, it's viable, but it's just how many
If you're Facebook.
how many machines do you want, right?
Yeah.
So you can do this in real time, like if you do GPU accelerated transcode or something like that. You can probably get like multiple viewers on a box, you know, in the tens. I would not necessarily say in the hundreds or the thousands or something like that. So that's pretty hard. If you're talking about accelerating or doing the real-time, what's it called? Real-time transcoding. You could do real-time where you just, in real-time, transcode the different viewports, right? So you have 10 or 30 or something like that. And you know, the source streams in the video, and then it splits it into 10 different encoders, and those things encode in real time, and then you have those outputs that you can switch to. So I think it's doable.
So you could potentially do like one field on a single machine, or would that have to be
In real time?
distributed? Yeah.
Yeah, absolutely. You could probably do multiple, depending on how efficient your transform is. And so that's another thing. The transform could be very costly, right? So first of all, you have how many frames of video are there. Then for each frame of video, there's generally 3 color channels. And you have X number of pixels width and Y number of pixels height. And then in our solution, for each pixel, we subsample to get multiple input pixels that we average together. So it quickly becomes like this huge, like I think it's order n to the 5th problem to try to do. So any little tiny optimization you can do there to make it faster actually makes super huge impacts.
Cool. All right. Thank you.
Hi, I'm Katrina from 360 Fly.
Hi, Katrina.
You were talking about being able to upload the 360 videos onto Facebook. Do you guys have the specifications for that available yet, or when? Yeah,
I think there's like a page, like a help page on Facebook to say what the specifications are. But essentially, if you take like a 4K equirectangular video and you append the proper metadata to it to say that it's a spherical video, then we'll handle that and process it just fine. You can like search on the internet for like spherical metadata tool or something like that. And most people that are uploading these to other platforms like know what that is. And we take that, we understand it, we'll encode it, and we'll serve it.
And the cube mapping that you were talking about, are you guys releasing any information about that, or do you have more details about like how it's supposed to work and stuff?
What kind of detail do you want to know beyond what was here?
I just didn't get to capture a whole lot of it, and I just want to be able to look at it later.
Oh, I think so. I think we'll probably talk more in detail about what we're doing, like a tech blog or something like that, to say, here's how it works. Whatever we really want to do is like open source to transform, so people can see here's actually how it works, both like cubes and pyramids and whatever. Because in actuality, all we're doing is building like a mapping table from output pixel to a set of input pixels. And whatever geometry you put in there, it doesn't really matter. And when you actually do the transform, you're just like, OK, I'm at output pixel XY. What are the input pixels I need to average? And that's it. So yeah.
Thank you.
Hi, I'm Ben Lang from Road to VR.
Hey, Ben.
And just wondering if there's any ideas about timeline on when we'll actually be able to view the 360 videos on Facebook into a headset.
No timeline that I know of. But it would be cool, right? That would be awesome. Cool. If there's no other questions, I think we're super on time. So thank you very much. Appreciate it.